Hello students, welcome to classroom. I hope you're all doing well. In today's class, we will be learning about refraction through a rectangular glass slab. This is a topic in your textbook, and a very important topic also. So let us understand how refraction takes place through a rectangular glass slab. So let us continue with the glass. So refraction through a rectangular glass slab. Let us understand how refraction takes place through a glass slab. So the first thing that we have to do is draw ourselves a glass slab. So let us draw ourselves a glass slab. So let me try to draw a glass slab here. Since it is freehand, I wonder how accurate will it come out. But I'm just trying that it comes out all right. Let's just say that it comes out good. Yes. Pretty good, isn't it? So okay, now this is the glass slab. Okay, this is the rectangular glass slab. So this is our rectangular glass slab. We will just write glass slab, no need to write rectangular. So this is our glass slab. Okay, it's a very thick glass slab. Okay, now glass is a medium, that's why we're using this glass. Now the center of the mirror is here. Okay, let's give a name to this. Let's give it as A, B, C, D. Okay, you can use any name. Okay, PQRS, KLMN. Okay, I'm using A, B, C, D. Okay, from the very first letters of the English alphabet. So the center of the glass is here. So let me start at least somewhere here to the left. Okay, so I want to make this as the point of incidence. So I want to make this to be the point of incidence. So if this will be the point of incidence, then we know what will happen here. A normal will take place here, isn't it? So normal will take place here. This is the point of incidence. Okay, so now time to draw the incident ray. So I'll be drawing the incident ray. Okay. Okay, so let us draw the incident ray like this. It should be straight. I hope it is straight. It is not straight, so let me erase it. Okay, you use a scale. Okay, you use a scale. It will be better if you use a scale. Me, I'm doing with freehand, so my freehand is not so good. Okay, somehow this came out quite well. Okay, so let me use this. This is the incident ray IR. Okay, this is the incident ray. We can give a name. We can give a name to this. A, B, C, D has already been used. So this can be E. This can be F. So the incident ray has a name EF. Okay, if you are going to do a write-up, you will write let EF. Here EF is the incident ray. Okay, EF is the incident ray. We have given a name to the incident ray. The name is EF. Okay, then between the normal, this is the normal. Okay, normal. So normal, we can extend it till here also. Okay, N bar, N bar. This is N bar. Okay, N bar. Normal, N bar. Between the normal and the incident ray, what do we get? We get an angle. This is the angle of incidence. Okay, this is the angle of incidence. We already know about that. Now we will do one thing. We will draw the supposed path of light. So we will draw the supposed path of light. The supposed path of light. What is this supposed path of light? The supposed path of light is the path of light, okay, which the light will take if this glass slab was not there. Okay, which means if the entire thing was just one medium, then how will the light ray travel? Will the light ray not travel straight like this? Okay, so this is what we call the supposed path of light, which will be helpful towards the end. Okay, so remember this. Okay, that we will be needing this also later. So we can always show from the beginning also. So just show from the beginning. Okay, so let's try to connect these two dots now. So you have to do this with a dotted, because this is just a supposed now. Don't make it continuous. Okay, just a dotted will do. Okay, I hope it's quite straight. All right. Okay, so this is a supposed path of light. No need to write anything, just keep it like that. Later towards the end we will be needing this also. Okay, so this is the supposed path of light. This is the path of light which this incident ray will take had there been no glass slab. Okay, but now there's a glass slab, So now two mediums are at play here. This is air, yes, before I forget, this is air, then inside we have glass, and finally again we have air. Okay, so we have air, glass, air. Okay, so we are here right now. The incident ray is in this medium, air. What type of medium is air compared to glass? Is it a rare medium or a dense medium? Glass. Air is a rare medium. This is a rare medium. And what is a glass? Glass is a dense medium. So now the knowledge of how light ray travels, okay, when it enters different media will be very much helpful here. So we are here. This is the point of incidence. So bending will take place from here. So now the incident ray is traveling from rare medium to dense medium. So light is entering from dense medium to rare medium. How does light travel when it enters from dense medium to rare medium? From rare medium to dense medium. Do you remember how light enters from rare to dense medium? Okay, when light enters from rare to dense medium, there are only two things that I will ask you here. Does it bend towards the normal or away from the normal? What is the answer? From rare medium, it's about to enter to a dense medium. So the refracted ray, will it bend towards the normal or will it bend away from the normal? Which will be the answer? It will be towards the normal, isn't it? From rare medium to dense medium, light bends towards the normal. So the refracted ray will take this path. This is the refracted ray. Okay, this is the R. Okay, EF. Let this point of incidence be G. Okay, this is 90 degree. Okay, then G. Then you can give name to this one, H I. The refracted ray is HI. Okay, so between the normal and the refracted ray, we have an angle. This is called the angle of refraction. Yes or no? Okay. Then the refracted ray is here now. This is another point of incidence again, class. This becomes another point of incidence. Okay, so we have to draw normal again. So let's draw normal here. So okay, like this. You can extend this also till the up. It looks better like this. If you extend till the up, it looks better. So this is another normal. So and you can draw it as M. This can become M bar. Okay. Now this has become another point of incidence. So for this point of incidence, this will act as the incident ray. Okay. For this point of incidence, ray EF was the incident ray. Now again we are having another point of incidence. So for this point of incidence, who will be the incident ray? This refracted ray will act as the incident ray. Okay, so this ray becomes the refracted ray for this very point of incidence. Are we clear? Okay, so now here again, now what will happen? Now again refraction will take place. Now look at the story here. Now the incident ray HI, okay, is in glass. Glass is a dense medium, and now it's about to exit to air. Air is a rare medium. Air is a rare medium. So light is about to change its medium from dense medium to rare medium. So how will the refracted ray travel? Towards the normal or away from the normal? How will it travel? Yes, it will be away from the normal. Okay, so it will bend away from the normal. So it will bend away from the normal. So away from the normal. So normally how will it travel? This is the supposed path of light for this ray. This is the supposed path of light. It will not travel like this, away. Nah? So away, let it travel away. So let it travel away. Yes, I have to make sure that this is parallel again. But in my case, yes, it's very close to it. So now I have to make sure that the emergent ray travels parallel this one. Okay, so I have to watch this one. Okay, like this. Okay, can be a little more better. Needs a lot of practice, class. So we have to practice. I have to show that it is parallel to the supposed path of light, or else I won't be able to tell you a very important point here. Is it parallel? Okay, let's just take it as parallel. Okay, so it should be parallel. Okay, yes. So at this point of incidence, okay, light enters from dense medium to rare medium, so it is bending away from the normal. Okay, it's bending away from the normal, not towards the normal. If it was towards the normal, this ray will be drawn somewhere here, closer to the normal, but it's going away from the normal. You want to see closer to the normal? Look at this one. This is bending towards normal, okay, and this is bending away from the normal. So normal and this ray, an angle is made. This is called the angle E. Very important. Angle E is the angle of emergence. Angle E is equal to angle of emergence, means the angle which the emergent ray. Now this becomes the emergent ray. So I is there. This can be the point J, and this can become the, this is the emergent ray, isn't it? Or why am I drawing in dotted line? Sorry, this has to be in bold line. My bad. Okay, so this has to be in bold line. Okay, I should not be drawing this in dotted line. This should be in bold line. Okay, this should be in bold line. So I, J, then we'll give a name K, L. So ray KL is the emergent ray. Angle E is the angle of emergence, which means the angle which the emergent ray met with respect to the normal. J is the point of incidence. HI is the refracted ray inside the glass. Okay, RR is the refracted ray. Okay, then G is the first point of incidence on the surface AB, on the plane AB, and J is the second point of incidence on the surface DC. Okay, angle I here, this is the incident ray IR. Okay, the incident ray is the ray EF, the refracted ray is the ray HI. Okay, so if you give names like this, okay, and the order of the names, like I said, you don't need to memorize this, you can use your own, but make sure that you are able to remember what you're using. So at least A, B, C, D, okay, follow this clockwise direction, and here you can start from anyone. I just follow the pattern A, B, C, D, E, F, G, H, I, J, K, L, M, N, like that. Okay, so it's easier for me to, okay, use a sequence. You can also do that. Okay, you can also do that. So now where do we go? Yes, we go here. Now see, oh, look here now, this one. So look at this. This is the final emergent ray coming out of the glass slab, and this is the supposed path of light. If we look at the supposed path of light and the final emergent ray, okay, we find a gap. We find a gap between this. We find a gap between the supposed path of light and the emergent ray. Okay, and if we look carefully, this gap is parallel. Okay, that means the distance is equal at every point. Okay, so it should be parallel. That is why I was taking my time. Okay, I was projecting this. It should come out parallel, or else how will I explain to you? So it should come out parallel. If you are doing with scale, then I guarantee you will get parallel. Okay, if you do this diagram, with scale and pencil, you will get yourself a perfectly parallel line. Okay, so remember, it should be parallel, so do the necessary adjustment. Okay, so now what will happen? We'll draw a perpendicular between this line and this one, between the supposed and the actual emergent ray. Okay, a perpendicular is drawn, and this gap between the supposed path of light and the actual emergent ray, this is called lateral displacement. Okay, this is called lateral displacement. This is called lateral displacement. Okay, this is called lateral displacement. It is represented by small letter d. Okay, so what is lateral displacement? So I'll write down what is lateral displacement. This definition will be useful. So where do I write? I should write it that side, I guess, or maybe I'll write it here. So lateral displacement, I have to give you the definition of this one. So lateral displacement is a simple definition. So lateral displacement, it is the distance between the actual emergent ray and the supposed path of light. Simple. This is it. Okay, the simplest definition, okay, that you will ever get. Lateral displacement is nothing but the distance or the gap. You can also call as the gap. Okay, instead of writing distance, you can substitute it with the word gap. So lateral displacement is the gap between the actual emergent ray and the supposed path of light. Okay, this is called lateral displacement. Okay, lateral displacement is also known as optical shift. This is also known as optical shift, or it is also known as optical shift. Okay, it is also known as optical shift. Maybe it may be important for you. Okay, so lateral displacement is also known as optical shift. Okay, now why is it called optical shift? See, it is called optical shift because, okay, if I extend this line like this here, now I hope it is still visible. Okay, maybe it's visible. So then a person keeps his eyes here, let's say. So a person keeps his eyes here, okay, and he tries to see this object. Okay, so the object, so this is light, isn't it? Light always comes from an object. So there's an object here. So there's an object here, and he tries to see, the object. Okay, thinking that it will be visible from this. Okay, without having good understanding of refraction, he says that he will see because he saw the object here. Okay, so he's thinking, okay, that he will see, he may be able to see the object from here. So he keeps his eyes here. So do you think he will be able to see the object? No, it's not. He won't be able to see the object. Why? Because light is not even traveling through this path. Okay, light is not traveling through this path. Okay, so he will not be able to see because light did not travel through this path. Okay, so where will he see the object? He has to bring his eyes, he has to shift his eyes from this position to this position. So he has to shift his eyes from that position to this position. If he shifts his eyes from that position to this position, okay, then he will be able to see this object. Why? Because this is the path of light, isn't it? Okay, so wherever we keep our eye, and okay, wherever the path of light is there, and if we keep our eye there, we will be able to see. Whenever light enters our eye, we see object. Okay, whenever light doesn't enter our eye, we do not see the object. So we see objects because the light reflected by the object enters our eye. Okay, the light coming out of the object enters our eye. That's how we see object. So this fellow, this eye can see the object, but this eye cannot see the object. So what he has to do is that he has to shift his eye from this position to this position. That's why this is called as optical shift. Optical shift. Our eye is an optical object. Okay, so optical shift. You cannot be viewing the object from here. You have to shift it here. So this is called optical shift. Okay, okay. The gap between them is known as lateral displacement, or sometimes it is also known as optical shift. The reason I have told you why it's called as optical shift is because you have to shift your eye from this position to this position. Okay, along the line of lateral displacement. So this is it, class. Okay, everything about refraction through a rectangular glass slab. Okay, so if you have understood this, in exam this question will come for 3 marks, and in the 3 mark you may have to do some write-up. So how do you write a write-up? Whatever you have understood, write it in the form of a story. Okay, write it in the form of a story, in the form of sentences. Okay, you don't need to memorize anything here, just understand. Okay, understand the story, how we do the leveling and how things are happening. All you have to do is just write them down. Okay, and then get some extra marks. So no need to panic, it's very easy. All you have to do is give it a shot. Okay, once you give it a shot, I guarantee you, you'll find that this was much easier. Okay, so everything is difficult, okay, if you don't try, but keep trying and trying and trying. You never know, you can become a professional. Okay, that's how the world is. Okay, so do not give up. Okay, keep trying, keep working hard until and unless you all achieve your goals. So with this note, we'll end the class today, and I'll see you again very soon in the next video. Till then, stay blessed and God bless you all.